So what are we going to talk about today? We're going to start with looking at ML.NET and its history, and then fairly quickly transition into uncovering the concepts behind the buzzwords machine learning and deep learning. Although ML.NET makes machine learning a lot easier than before, it's important to know some of the basics to follow along in discussions as well as when building out your code base. Once we have a good understanding of the concepts, we will take a step back and look at the overall machine learning workflow that we can use to train our own model. My hope is that we'll spend about half of the time on this talk to go through some live coding and make sure you get to see this in action. So, why should we be excited about ML.NET, and why has Microsoft spent so much time developing this library? Well, frankly, because it allows me to put the words in this slide together, machine learning in the .NET space, two separate sets of domains that commonly have not been associated with one another. Machine learning has, for a long time, been fairly foreign to software engineers, and especially those working in C# or F#. The dominant languages to use when training your machine learning models are Python and R. Although both of these are fantastic languages and rightfully popular, it causes problems for the .NET developers, as we not only need to learn totally new concepts in the machine learning domain, but we also need to learn one or more new languages. Machine learning models written in R and Python doesn't integrate that well with our existing DevOps pipelines, nor are they easy to integrate into your existing application and to consume. So to solve this problem and to enable the .NET developers to take advantage of the opportunities AI and machine learning offers, Microsoft spent tons of time into developing ML.NET and has released that to the public. So ML.NET, as I already said, is an open source library. You can run it on Windows, Linux, or Mac, and you can also contribute yourself as it's open source. You can submit issues and pull requests to GitHub. A key differentiator from other machine learning products in Microsoft's catalog is that it allows developers to build custom machine learning models as opposed to pre-trained models offered by, let's say, Azure Cognitive Services. The framework is also extensible, meaning that you don't need to train all your models in ML.NET before using them, but you can also leverage pre-trained models you may get from the internet. ML.NET was released to the public at MS Build in 2018 and was just released for general availability at Build 2019. A really exciting feature that I want you to be aware of is AutoML that's currently in preview. It really makes the learning curve to pick up machine learning a lot less steep. Actually, I had the pleasure of trying that out just last week, and it's just blown away how simple that is to use and how easy things get. And I hope to have some time today to actually showcase that as well in our demo. So ML.NET can do tons of stuff. This slide is actually just a copy of the ML.NET homepage, showcasing some of the things the framework can do. I just want to get your attention to the fact that we can do all kinds of things here, such as sentiment analysis, product recommendations, and price predictions. Simple machine learning tasks that ML.NET makes very easy to do. If anyone is aware of Azure Stream Analytics, you will also know that we can do anomaly detection in that framework, and that is actually powered by ML.NET. One thing I want to point out in this slide is that you see ML tasks such as image classification here as well, and object detection. We will touch upon this later, but these are deep learning tasks, and ML.NET currently doesn't support you training your own deep learning models, but it allows you to integrate already trained models from other frameworks, such as TensorFlow. So, is ML.NET already used today? And if so, where? Well, surprisingly, ML.NET has been used internally at Microsoft for many years, and has just recently been released to the public. PowerPoint is already using ML.NET under the hood, and this slide was actually designed by the framework. I just dropped all the icons randomly on the slide, and ML.NET suggested the way it should be organized. You can also find ML.NET in other products, such as Excella. If you ever seen the chart recommender for sort of data, that is ML.NET under the hood as well. Windows 10 uses ML.NET for Windows Defender, and I believe Outlook is also using ML.NET as of late. So the machine learning landscape is very competitive. There's a flora of available options out there, depending on your needs, and ML.NET is just one of many options. Some of you may be familiar with Azure Machine Learning Studio and Azure Machine Learning Service. You may find these products to the left of the slide, together with cognitive services. These technologies are in general easy to get started with, but offers you less control, as in particular Azure Cognitive Services, which predominantly offers pre-trained models that you may pay to utilize. This may be great for many scenarios, but if you ever want to build a custom model based on your own data, those services will not be enough. This is where products such as ML.NET comes into play, which allows you to build completely custom machine learning models based on your own data. Although it is slightly more difficult to master, they provide you with the control you need in many real-world scenarios. So, for anyone interested in getting involved in the community after this session, I strongly recommend you visit ML.NET's GitHub page or repo that contains fantastic samples using ML.NET. That's definitely the fastest way to get up to speed to this framework, is to use the samples and to follow the tutorials. So what is machine learning? Well, machine learning is all around today, and you can see it in everything from a simple application, such as a spam filter, to your inbox, to your Google Home or Alexa. It's commonly used in medical diagnostics, self-driving cars and stock market analysis, and various recommendation engines such as Netflix or Spotify. Facebook and Google are by far the market leaders in this sphere, although Microsoft is quickly catching up with frameworks such as ML.NET. So defining what machine learning is not a trivial task. There have been many definitions of what machine learning is over the years. A prominent figure in the machine learning space in the 1950s, Arthur Samuel, defined machine learning as the field of study that gives computers the ability to learn without being explicitly coded. What machine learning is really all about is teaching a mathematical model to make decisions on real-world data in such a way that it can make accurate predictions on incoming new data that the new model was trained with. We can, for example, train a model on a large number of animal pictures in the hopes that our trained model will from now on be able to detect if a specific animal is in a picture or not. Artificial intelligence experts argue that machine learning is the best way forward towards human-like AI, which is the final product we want to achieve. So the different types of machine learning, the two most common ones that you may have heard of is supervised and unsupervised learning, although concepts such as reinforcement learning also exist and it's very popular. In supervised learning, we are doing our best to teach the computer to do something specific. At our disposal, we not only have the data necessary to train a model, but we also have the known answer, often referred to as a label. And we'll get back to that concept a bit later. A good example of this may, for example, be creating a model that classifies email as important or not. And in order to create this model, we would need to have a large set of emails already labeled as important or not important. We should then be able to use a supervised machine learning task, such as classification in the slide, to train our model on, and creating a model that can accurately predict and label emails going forward. Unsupervised learning is the case where the correct answer is not known, and the computer teaches itself. And examples that is clustering, principal component analysis, anomaly detection, and you can use them, for example, to detect differences in a data set, but not necessarily label what those groups are called. So you may have heard the term train your model been mentioned quite a few times in this talk already. So what does that really mean? Well, training a model means to use a large scale data to accurately create a mathematical representation or a model of a real-world process in such a way that the predicted outcome is accurate as possible. In other words, we are creating a function, f here, based on variables x1 to xn that gives us an accurate y. In the machine learning world, x1 to xn are called features or a feature set, and the predicted outcome is called a label. Two very important terminologies here to keep in mind. To give an example, x1 to xn may be properties of the house, for example, number of bedrooms, square footage, number of bathrooms, while y may be the predicted price. We would then need to fit a function given those sets of input variables such that a house prediction can accurately be predicted. The algorithm used to create the function varies depending on what machine learning task you're trying to accomplish, for example, classification or regression. Although Excella makes it a lot easier to pick up on machine learning, I found it very useful to learn some of these basic terminology in the domain, as you will frequently see it referenced in the code and tutorials and other documentation. So how does machine learning relate to other commonly used buzzwords, such as artificial intelligence and deep learning? Machine learning is actually considered a subfield of artificial intelligence. Artificial intelligence is, so to speak, the overall umbrella for creating human-like AI, and it consists of a lot of science trying to make this possible. Although we have not yet created true human-like AI, as proven by, for example, the Turing test that you may have heard of, machine learning is considered a central piece of that work. So you may have heard of deep learning and neural networks being a hot topic in the news as of late. So deep learning is actually considered a subfield of machine learning itself. There have been lots of fantastic breakthroughs recently in the deep learning space, and we have much to thank deep learning for innovations such as computer vision, speech recognition, natural language processing, and so much more. So although this talk focuses mostly on MLNet, I want to take a couple of minutes just to give you a layman's overview of what deep learning really is. So deep learning can be seen as machine learning on steroids, and it's commonly implemented by a concept called artificial neural networks, or ANNs. So ANNs consist of a number of simple nodes or neurons organized in a deep layered structure. Each neuron is connected with other neurons and performs a designated function. The importance of that specific function or neuron is controlled by multiplying the input value with a given weight and adding a bias. And I try to illustrate that in this slide here. Each type of neural network will have its own specific features or structure, and structuring the neural network in different ways is actually beneficial depending on what problem you're trying to solve. For example, computer vision or natural language processing may have different structures of the neural network. Neural networks are very powerful as they allow the computer to explore or find patterns that are too complex to manually extract or to teach a computer to recognize. Neural networks as a concept is actually nothing new. It's been around for quite a while. It's just until recently, though, that the computer power to train these models exists, as well as the vast amount of data that is needed is available. Training a complicated deep learning model can actually take days or much longer, even with today's fantastic hardware. So the way a supervised neural network learns is through a process called backpropagation. So what that really means is that in a given scenario, when that's run through the neural network during training, at each time the neural network reaches the output layer, it will calculate something called a loss function. So this is simply just a function to determine how far away its predicted outcome was from the correct answer. Remember that in supervised learning, we actually know the correct answer. So based on how far away the correct answer the model was, it will perform a process called backpropagation and automatically adjust its weights and biases to attempt to reach a more accurate prediction. So as I said, MLNet doesn't currently support training your own models or deep learning models, but it does support integration and consumption of already trained models. And the most commonly used frameworks to train deep learning models in is TensorFlow, which is Google's flagship. So if you're interested in deep learning, there are some great resources out there to learn, and you can interact with deep learning algorithms yourself to see how they work. So to give an example, I have actually recorded an interaction that I had with one of Google's experiments that you can find online. And this application will give you about 20 seconds to draw something, and the computer or the deep learning model will try to figure out what it is. And its guesses will be displayed on the lower part of this slide. So just to show you how that can work and how you can get involve yourself in this, you can see here that I'm trying to draw a flag. And the machine learning model here, the deep learning model, fairly quickly figures out that this is a flag. The next challenge is an Eiffel Tower, and I was amazed how fast he was able to pick an Eiffel Tower based on my fairly bad drawings. The barn, though, drawing a barn definitely proves to be difficult, because barn, it could be a house, it could be a cottage house, it could be an apartment, it could be so many things, and I am by no means Picasso. As you see here, it's really struggling to figure out what I'm drawing here. It's not a cooler, it definitely is a cottage, it's a stilt house, so it does fail to figure this out. So it's really fun. You can interact with the deep learning algorithms as you like online. There's tons of examples, so definitely check that out. All right. So we have covered most of the basics of machine learning now, but what is the actual process for building your own model in a framework such as ML.NET or even scikit-learn or another Python-based library? How do you get started today to build your own model? Well, the first step is to identify your problem. What are we trying to solve here? Are we doing text analysis, such as sentiment analysis or text classification? Are we trying to decide how many customers in your client base are similar in what way? Are we trying to create a model that can determine what breed the dog is, just based on an image? So depending on your problem, there will be different requirements and data you will need to collect, and as well as which machine learning task or training algorithm you may need to use. So once you have determined your problem, the next step will be to gather your data. And this is, in my opinion, the most important step of them all. The accuracy of your model greatly depends on the provided data. If the model does not have enough data to train on, you will not be able to make a good enough prediction. Similarly, if the data is biased or skewed, the prediction will also be biased. And this is currently a hot topic in machine learning AI, about biased data, biased models. I definitely recommend you to check that out as well. But let's say you, for example, are training a model to determine the likelihood of a person committing a crime, but your data only contain individuals convicted of a crime from a specific demographic. Doing so will create a biased model, as the model has been trained that this specific group is more likely to commit a crime, although the data may not be representative of the overall picture. But overall, in this step, what you want to make sure is to capture as much data as you can and make your data set as wide as possible, so you can try to account for any known variance. So make sure you capture all the variables you have, even though you're not sure yet if they will be important or not. So once you collect your data, we want to divide it. So this is a common practice when working with machine learning, especially with supervised learning, and that is to split your data into two buckets, usually at a ratio of about 70 to 30% in each bucket. So 70% of your data will be used to train your model, while the remaining 30% will be used to kind of test the accuracy of your model after the model has been trained. We will see how this is done in practice once we get started with coding in ML.NET in just a little bit. So machine learning models or algorithms are very, very picky. They do not like dirty data, and they only work on float vectors. So we are tasked with the job of transforming our data before we can have our machine learning algorithms work on it. This is a very important step, as this is where we ensure data quality going in. So common things that we normally would like to do here is to replace any missing values in the data column or normalize variables to a value between 0 and 1, which is what machine learning algorithms generally work best on. We also want to make sure to transform non-float vectors to floats. So we can do this, for example, with a technique called categorical one-hot encoding. One-hot encoding takes a non-float variable. Let's say, for example, the make of a car in a data set. So the data set may contain tons of rows about people and what car make they have, all Audi, Mazda, Mercedes, Hyundai, all those things. So one-hot encoding can then transform that column to, instead of having a string as your value, it can be to multiple binary columns, say, is Mazda with a value of 0 to 1, is Audi with a value of 0 to 1, and so forth. This offers a huge performance boost for a machine learning model and transforms the data to a language that the algorithm can understand and work on. So once you have your data in a neat and clean format, it's time to train your model. Training your model basically means choosing which algorithm to use when attempting to fit your data. So there are tons of alternatives out there, some are better than others in different scenarios. You may, for example, want to use an average perceptron for binary classification cases, while others are available for clustering or regression. At first, and especially this was the case for me, it can seem very daunting to know what algorithm to choose here. And I just want to make a couple of quick notes on that. Firstly, the process involves a lot of trial and error. Once you train your model, you will be able to measure how accurate it is. And if need be, you can just go back and choose another algorithm. It's that simple. Secondly, the Microsoft documentation is very useful to help you navigate which algorithm or algorithms to choose in which scenario. So definitely check that out. And third and lastly, techniques such as AutoML, so automatic machine learning, which ML currently supports in preview, completely alleviates this process as it automatically discovers which learning algorithm best fits your data set. This is super exciting. It's currently only supported for, I think, classification and regression, if I'm correct. But they're working on rolling this out for other machine learning problems as well. So we have trained a model, and we now need to measure its accuracy. So training a model based on data by itself is not sufficient. We need to have some kind of quality control here to make sure that what we have created actually also makes accurate predictions. It's not useful to have a model that predicts house prices if it predicts $3-4 million more than what it's supposed to be. This is a step of evaluating your model. And what we'll do here is we'll use a test data set. So remember the 30% we stored from earlier, and we will use our training model to run through that data and then measure a percentage of the cases which were accurately predicted. And that'll be your accuracy. There are lots of other measurements as well, depending on what learning algorithm you choose to evaluate your model's accuracy. But the accuracy one overall, I think, is one of the most important ones to keep in mind. So once you're happy with the accuracy of your model, it's time to put it to work. And this is one of the beauties with MLNet, as it allows us in minutes to deploy a model to, let's say, an ASP.NET Core application. You can put it in the cloud as an Azure function, or you can integrate it into your on-premise or desktop .NET application. And this is really one of the great things with MLNet. So once the model is in operation, it is important to monitor the performance of the model and iteratively evaluate and improve it with more data as needed. A good example of this, for example, would be to kind of monitor if a user marks an email as a spam or not, if you're doing a spam filter, I guess, for machine learning. If your algorithm did not capture that specific email that a user marked as spam, you want to make sure you track those things so you can train your model to become even better and in the future detect those kind of spam emails. So if we apply this workflow to ML.NET, how would it look? So if we take the machine learning context and look at how each part can be translated to the features and functionality of ML.NET, what do we really get here? Well, firstly, we have to make sure that we have identified a problem correctly, and make sure we have gathered data as well in a format that we are happy with. Once we have that, we can use ML.NET to start working on our task here. The first thing we will be doing here is loading our data into memory, into application. That can be done from all kinds of places. So, for example, through a text file, which is one of the more common scenarios. You can load from binary, from a SQL database. I believe you may also, for large sets, load it over streaming as well. So one thing to keep in mind here, and we'll touch upon this in just a little bit during the demo, is that there are two concepts in ML.NET that we should be aware of. The first one is the ML context. So ML.NET implements something called the ML context, which is a kind of catalog or a main construct that you can use to find all of these methods to load your data, transform your data, train your model, and so forth. It contains all of this information here, and you will need to create one of those ML contexts when you start training a model. Second of all, ML.NET uses a concept called pipelines. Data pipelines, training pipelines. It's actually not that complicated as it may sound. It's just a concept to make sure you have objects that you can append things on top of. So you may start by creating a data processing pipeline based on your loaded data, and you will then append a transformer or transformation to replace missing values. You may then append another transformation on your pipeline to normalize vectors, variables, and then you may append another transformer to select which features to use in your space here. So that's really cool. That's some concept you definitely need to know about, and we'll definitely touch upon that in just a little bit. Finally here, what I want to mention in this slide is that once you train your model, where does it go? How does it look? So if you're familiar with other Python-based libraries, there are different formats as they get outputted to. ML.NET outputs this data as a zip file. And you can deploy that zip file to blob storage. You can include it in your application. You can do more or less whatever you want with it. The only thing you need to do in your application is to load it up again, and there you go. So pretty simple. All right. So I have been speaking way too much here already. We have about half of an hour left. So I want to take some time now to focus on our code example here. You can see this, how this works. So one thing what we're going to do here is we are actually going to focus on a very simple problem. And the reason why I want to focus on a simple problem is because I want us to really focus on the machine learning workflow, all the things you can do in ML.NET, and not necessarily be sidestepped by a complicated machine learning example here. So what we're going to do is to look at the Titanic. And you may be aware of this, of course. I mean, everyone has seen the movie, I think. But the Titanic sunk in 1912 on its maiden journey between Southampton and New York. About 1,500 of the 2,200 passengers on the ship died, unfortunately. And there's a lot of information and data on the passengers from what passenger class they were part of, their name, if they have siblings aboard, all kinds of things here. So we can train a model using that data that's publicly available to predict the chance of survival on the Titanic. And we can then, if we want to, deploy that as a function or do other things. So that's kind of what we'll start doing. So I'll switch over to the data here. So what are some things we want to do here? So we, if you think back about the overall workflow here, we want to identify a problem first. We have done that. We are trying to predict the survival chance of any passenger. And after we've done that, we want to gather data. The data is right in front of you. It's in this Excel file here. So let's take a look first and explore the data that we have here and kind of see what we're working on. So the data is pretty broad here. We've got tons of passengers. Each passenger is defined by a column for survival. So 0 if they didn't survive, and 1 if they survived. P class is a bit cryptic, but it stands for passenger class, so third or first. Name, if they were male or female. Age they were, siblings on board, so these are a number of siblings and spouses aboard, and parents or children aboard, and also the fare they were paid. The thing that you want to see directly here is that we have missing values. So Williams Henry Allen, for example, we don't know how old he was. We don't have the data. We didn't have a data accuracy back in the day. So that's definitely something we would need to address when training a model, because having a missing value in a column can really skew the overall model and the accuracy of it. Other things to note here as well is that we have non-float variables. Name and sex here, they're not float values. We can make all these float values, that's fine, but we cannot make this a float value. So we need to implement something we talked about, which is one-hot encoding before we can train a model using this data. All right, so let's get started. I have created a simple application here that is just a .NET Core application. It's completely blank, as you may see here, so we can get started from the beginning on how we will actually train a model to predict this. So I may actually not have mentioned this as part of the presentation, and I should have done so, but ML.NET is actually supplied as a NuGet package, which is very convenient, of course. So the first thing we want to do when training a model is to download a NuGet package. So currently we have the general availability 1.0 release here that was released MS Build a couple of weeks ago. So we'll go ahead and we will install this package. Cool, awesome. So that's perfect. And what we want to do here is to structure our training here in such a way that makes sense to us. So the first thing we want to do here is obviously then loading our data in memory. If you remember, the second thing we wanted to do was transform our data. So let's say transform to make sure that it's in the correct format and the way we want to use it. The third thing we want to do here is to train our model. So we want to fit a machine learning function in such a way that it predicts the data accurately. And to make sure it holds the quality we want to evaluate the model. And after that, we can, of course, save it to a zip file as well, and we do tons of other stuff. But let's add these comments for visibility. So before we even start loading our data, I spoke about the fact that we need something called an ML context. So, and that is where all the things reside on all the catalogs, all the transformers, everything resides. So we will start by creating one of these. All right. So let's just take a quick peek here on the ML context and see what it has. And we can look too far here, but that's fine. Actually, we'll look at that a bit later, because I think that will take away from the concepts here. So we create an ML context, and this is going to be living with us and help us do all these things. So the first thing we want to do here is to load our data. And we can do this using the ML context. And it is in a catalog called data, so it's very convenient. And we want to load it on file, because this is a data file. This is a CF, comma-separated file. And we can do it load from text file. All right. The first thing we notice here is two things. One, we need to, of course, include a file solution. So let's start by doing that. Let's create a folder called data. Let's go and add this into our solution. And this will be under Titanic, I believe. And make sure when you do this, make sure you change it to copy always, because that's going to make sure that it runs properly when you train your model here. Awesome. And we need to define the path, of course, for this. Let's do that here, maybe. So we will say function string data path, and it's going to reside under here, I believe. See if we can get this working. All right. So we can pass this in here and let ML context know where it is. It's not as simple as this. One thing we also need to define here is the schema of the data. So what columns do we have? What orders are they? And how can we work on them in ML.NET? There are tons of ways to do this in ML.NET. I'm going to show you one of them, which I think is convenient, but this is not the only way you can work with this. So what we'll do here is we'll create a schema class here. And for anyone familiar with the framework, it's pretty similar to that framework as well. Similar concept, but not exactly the same thing here. So we want to create here is a passenger class, because we want to be able to hold the data for each of this row in memory and load them. And not to bore you with too much of this, I'm going to copy over the schema, so I don't have to write a lot of properties here when you're listening. And I will talk about them a bit. All right, so as you can see here, we have a property for each of the columns in the dataset. survived, passenger class, name, parents on board, all those things there. They're all part of this, and we define the schema this way. The key here, and the magic number, is a load column. Load column is a declaration of each property where we wish to define the index of these columns in a data set. So we all know that survived was column 1, for example. So that's how it works. Awesome. So we can generically then define the schema like this, and we will have our data in a format that works well for us. That's really cool. The second thing, as I kind of skipped over, but I'll touch upon right now, is the fact that we want to split our data into training and test data set. You can do this yourself if you want to. I have 2 files, one for training, one for test, and you can do this split yourself. But I actually prefer doing it using Untitled.net's built-in support, which will provide you with an object and the data split for you. Again, you can go to the data catalog and you can call something called train test data split, and we can pass in the data here to use. Perfect. And also, before I forget this, I kind of always forget this, is that we also have to define more here than just the schema and the path here. Because as you saw, we have headers in this data set. So we have to make sure we let the framework know that do not parse the first row here. And we also want to ensure we let Untitled.net know what the separator char is for this data. And it's going to be comma separated. All right. I think we're good there. So we have loaded our data and we have split our data. So let me do this just so we can see the work here. Loading. The next step here is to transform our data. And when we transform our data, we want to make sure that we do all these things here that we talked about. We want to replace any missing values in the age column, firstly. We want to convert that sex column, female or male, into, or this gender column, into a float vector that we can understand. So we can use one hot encoding for that. And lastly, we want to concatenate all of our feature set here, all features, passenger class and so forth, into one feature vector, one float vector. And that's all done through transform step here. And this is where pipelines come in. So we can create something called the data process pipeline, for example. And on the ML context, we can use transform catalog here instead and access something called categorical one-hot encoding. Super good. And what we pass is the output column, and we can just overwrite the existing one as well as the input column. So we want to do one-hot encoding on this gender column to make sure it's converted to something that Untitled.net can read. Then comes the magic here. We've created our pipeline, and we can now start appending things. Let's append more transformers. I think this is really cool. So we can append, replace missing values, for example. So we talked about the fact that we wanted to replace any missing values we had in the age column, right? So the column that we want to output here is going to be age, or that's the input as well. And we want to define the replacement mode here. So there are many ways you can do this. Let's see. As you can see, you can either define a default value to replace any missing values with, a maximum or a minimum or a mean value based on the column overall. Depending on which data you have or which column you want to replace values in, you can choose different things here. For us, we'll go ahead and choose the mean here, as it makes the most sense. All right, and so we have done that. So the last thing we want to do in the transformation step here is to concatenate our features that we want to use for predictions, and we want to create a features column here to use. So again, we can use the transform catalog and ML context and call the concatenate function here, and we'll say that please output this into features column, which is the kind of default thing here, and please pass in and concatenate values from these columns. And let's just use a couple now, try with here. So we want to do passenger class. I think that will account for some variance. We'll do the gender column as well. And let's see, to make sure I can spell these. We want to use siblings of board. Into my first language, I need to check the spelling here so I don't misspell it. Because these obviously will work differently here. Sibling board. And we can also finally pass in, I guess, parent support. All right, perfect. So let's have a little recap here what we've done here. We created the pipeline here for data processing. We are in the pipeline here, we are replacing the gender column with one hot encoded version of it. We are then looking at the age column and making sure that any missing values are handled. And we then concatenate all the features in a feature set to a features column. Awesome. All right, so that was pretty quick, right? Not too much code to write for doing all those things here. So let's get into training here. We want to train our model now to make sure we fit it to the best way possible. Training, boom, boom, boom. So we can then create a training pipeline instead and use that concept here. And that will more or less just be the same pipeline as before, but now it's in a different context and usage, and that's why you have a name change on it. And what we can do here is to make sure we append the trainer or the algorithm we want to use here. And again, this is about trial and error here. There are some documentation on the Microsoft homepage for this, so don't feel like this is a big task. It's actually easier than you think. But again, this will be on the ML context. And for those not aware, I should probably mention this earlier. What we're trying to do here is binary classification. So classification, we only have two options. It's binary. They survive or they do not survive. Multi-class classification for labeling GitHub issues or something else is different. This is binary classification. So we will find our trainers that we can choose from under the binary classification catalog. And if you're unsure of what ML tasks they're doing here, again, just look up the documentation and you'll be good, no worries. So we are not going to use calibrators. We're just going to use trainers here. And this is where all those exist. And we're going to use logistic regression for this case here. And when we do that, we need to pass in what column we are going to use as our predicted value, our label column here. So again, you see that ReSharper gives us this label column name to help here. So knowing your terminology here, like labels, is important as it will simplify how you interact with the framework as well and understand what it's asking for. Cool. All right, so here comes the magic. Now we want to create our train model here. So train model. And this is using the training pipeline, which also has the data processing pipeline in it now, to fit our data. And we fit our data with a test train data set, train set. So again, we will use the training data to make sure we create a model that is accurate as possible. Awesome. All right, so we're almost done getting a model trained here. The next thing we want to do here is evaluate the accuracy. And what we're going to do here is we're going to use a training model, pass in the test data set, and transform that, and then using an evaluator for binary classification, measure how accurate this was. So we can call this predictions. And on our trained model, we will transform our test train set, train here, and we will use an evaluator to get some metrics here. And the evaluators, as you may already have guessed, is going to be on the ML context. And it's for each ML task, you have a different set of evaluators. So binary classification has their own. And we'll pass in the predictions. So what the trained model was able to predict, I guess, for the test set here. And we also need to define, again, which column we are using as a label here. Cool. So let's actually debug this and see if our solution builds and creates something. If it does not, I apologize. It's definitely possible. Let's see here. We'll put a breakpoint in there. Good. All right, awesome. And I'll just show you this as well. We have our command line prompt going here. All right, so we actually were able to train our model here. And we have a train model, we have a pipeline, we have predictions. Let's see how well it was able to predict this. We have something called a metrics column here. And this is actually pretty cool here. So you have tons of properties here you can see. It may be a bit small for you on the lines, sorry for that, but I'll read out the most important one here. It's the accuracy. And we can see here that we have 80%, so 0.8, 80% accuracy. It was able to correctly predict 80% of the incoming data in the test set here. We have other properties here that you may be interested in for some kinds, some cases. For example, we have positive precision and negative precisions. So how good was it to predict specific cases, such as when people did not survive and when people did survive. And once we've done this one time, and we'll go ahead and close this right now, you can, if you weren't happy with 80%, and it's not bad, it's not great, if you're not happy with 80%, you can go back here and just replace a trainer. You can go back here and change something with transformations, or use more input features here. See, we only used a couple here. We use more, and that will probably give us a better accuracy. So don't be too worried if your accuracy is not good. You can always adjust that. Finally, before I want to go show out ML real quick, we want to save our model. And I just want to show you how that's done. We're not going to look at that necessarily. But again, it's in the ML context. You will call something on a model, call save. You'll pass in your trained model here. And you also need to pass in the schema, so we can say that. And there you'll find our trained data set schema. And we have to name our model something, so model.zip. And this will be created as a zip file. And using another function on the model dataset, you can unload this saved and trained model in an Azure function or whatever, and create something called a prediction engine in one line, and then be able to very simply pass in incoming JSON, payloads, whatever you want to do here with the same schema, and get the predicted outcome on your data. So as you can see, we did this with comments and with console write lines here in less than 40 lines of code. I think it's super powerful. So we have a couple minutes left to just kind of leave you with something I think is really cool. I want to show you AutoML. So if you get started with machine learning, this can be daunting. What is the algorithm to choose? How to transform the data? It can be a lot of things you have to get worried about. To get started, you can use something called AutoML. And AutoML is automatic machine learning. You can, what it does is it allows you to leave everything of that to ML.NET, and it will pick the algorithm, pick whatever transformations make sense to your dataset, and output both which algorithm was the best, but also a sample console applications with code that you can keep using, as well as assemblies that you can integrate into your existing applications. Currently, they only support that. Well, this is currently supported for a Visual Studio tool that you can download from the market, but you can also use the CLI through PowerShell to train the model. And I wanted to just briefly do that here and show you the syntax. It's super simple. You download or install a command line interface, a tool here for ML.NET. You can then select, as you see here, auto train, define which classification task we're doing here. So we're doing binary classification. Define where the dataset is. So we're already in the folder here, Titanic, and we have a dataset called DLCSV. What index is a label column on? So a 0 as headers. And then the final thing here, which is very important, is the max expiration time in seconds. So currently, I'm just going to do it for 30 seconds to show you how it works. But if you want to, you can set this for minutes or hours, and it will keep just chugging through to figure out what the best permutation is. And each permutation, it will try different algorithms and try different transformations to get as good a result as possible. So let's put that, say, 4 seconds, and start this and see how it works. Oh, okay, great. Let's stop my Visual Studios instances here, because I think that's holding up the file, as well as our file itself here, and try that again. All right, that's working. So you can see here, it's chugging away now for 40 seconds, and the current best accuracy we get here is 82%. We had 80%, if you remember, in when I was doing myself here. So already after a few seconds, I was able to find a better model than I did. Not so hard, I guess, but it still did. And it will show you which algorithm it's currently trying and which algorithm it previously tried here. In about 10 seconds, it will output the result set for you, so you can have a look at for yourself here. Let's give it a few milliseconds here. Perfect. So you see here that the best trainer was the logistic regression binary here, and you'll see the accuracy. But it also shows you other things it's tried here, and other things it's done. And the longer you run this, more iterations, we have different results, and you will get a better model. Furthermore, it will output sample application here. And let's go look at that just briefly. Dump the console application right in a folder here where I had my data. And if it opens up, I did not intend to do it in 2017, but that's fine. So you can get this working. What it will do is it will create a console application for me, which uses the best algorithm that it decided that it was, as well as the kind of model and integrations to use this in a real-world example. So if we start looking at the console application, get it up here, perfect. You see that it's doing a lot of things that we already did, but it's doing it in a different way. I think I may have to get some things going here, but it's fine. But you see it creates animal context as well. It is loading our data a slightly different way, but still good. Actually, this is in the prediction part here. Let's see if we can get model builder. I think that's where we have it. You can see how it is loading from a text file here, and fairly similar way that we did it, some additional parameters. It's kind of building a training pipeline. I'm not going to go into this method, but it's doing similar things. It's also evaluating the model, and then training it and saving it. So a lot of things we previously did, but you will get a lot of these for free here. What kind of transformations does it recommend us doing? What is the algorithm it chooses for us? And so forth. So instead of doing this for half an hour, we did it in seconds, and we have an optimized model with code. So I really recommend you look at this. This is super cool. I can't wait to keep following this as it goes along. So with that, that's all I wanted to say. Thank you very much for listening, and I will turn it over to Morten.
All right, let's keep your screen rolling a little bit. Thanks for presenting, Alexander. We do have a couple of questions here. Some you may know the answer to, some may be too specific, but we'll go through them anyway. Is there an equivalent in ML.NET to Pandas data frame?
That's a good question. I'm slightly aware of Pandas data frame, but not in the sense that I feel comfortable answering that question. So I will defer that to this else that's more qualified, I think.
All right. Then another one is, are there any strongly typed versions of the transform that you showed during the presentation to avoid the use of magic strings? So
I don't think as of yet, I mean, I missed that, but one thing I thought of actually when I was writing that is you can use the name of the property instead, probably for the classes or similar things. But as you can see here, even the examples from ML.NET currently do not use any type ones. They're actually using strings here. And I definitely think that's something that can be improved. I also thought about that when I saw it the first time. And actually, what I suggest you do is, if you're interested, open up a PR or an issue at the GitHub page and see if we can get some improvements here. It's still an early stage, so definitely room for improvements.
All right. Another question that just came in, are there some wrappers or built-in F# friendly functions for this?
So I haven't explored the F# version, but yes, there is F# support as well. So, and there are also F# samples on the GitHub page, the ML.NET GitHub page. So if you're an F# developer, definitely check out those samples, and it will guide you into how to do that with a functional language.
All right, yeah, and then one more, probably a little bit too specific, but I'll give it a go anyway. Are there any examples or thoughts that you would consider using ML.NET versus PyTorch or scikit-learn libraries?
So the question was whether I would, which scenarios I would use ML.NET instead of scikit-learn, right?
Yep.
All right, so that's a very good question. So I think the reason why we have ML.NET and the reason why I like it is firstly because it really integrates well with your .NET stack. So if you're a .NET shop, definitely use ML.NET. It is production ready, has tons of support. It will make things a lot faster for you and do your DevOps pipeline better. It will integrate well in applications and so forth. The second argument I also wanted to give here is that there are lots of research and studies out there as of late here that shows that the runtime for training your models is actually a lot better in .NET Core and ML.NET than in equivalent Python libraries. If you're doing something like deep learning or want to train your own models from that, that definitely may be something you want to think about a bit. You can integrate already trained models in ML.NET. There's something called the Onyx standard. So that's a machine learning model standard for interoperability. So you can actually train your deep learning models in TensorFlow or something similar, and then port it to ML.NET and consume it in ML.NET. So it's a little bit more work, but if you have a .NET shop and that application, it's definitely worth it because you can use it out of the box then.
All right, perfect. And then the final question, like every single presentation you probably do, is there a repo or link to the source code that you've used in the presentation?
That's a great question. And I actually have a GitHub repo that I'm happy to share if anyone wants to message me on Twitter, or I can share it to you, Morten. But yes, I have a repo with this source code.
Yeah, okay. So everyone feel free to reach out to Alexander and then he'll give you a link to the sources. All right. I think we're through. Thanks for presenting.